I'm going to implement that in a moment, but just before I do, we already talked about many different representations of parsers. And I'm going to define many representations. So that means, of course, that I should have a class of parser representations. So I'm going to define my exactly operation as the only operation in this class. And here is the implementation for monadic parsers. All I do is wrap the monadic computation, which does just what you would expect. It reads the input, inspects it. If it's empty, we fail. It's a monadic computation now, so I can fail with M0. Otherwise, I look at the first symbol. I check that it's the token I'm looking for. I consume the token, and then I just return the result. Okay, so this is very similar monadic code to what we saw yesterday. So here is the parser, once again, now expressed in terms of the applicative functor interface. There's two differences. For a start, I'm now only using the exactly thing, so I'm only looking for exact tokens, just as a simplification. I actually need to add those type signatures up at the top, otherwise the compiler will not accept these definitions anymore. And you'll see that there's an AnyOf function in there, which I'm using now to recognize digits. And AnyOf is easy to define. I just map my exactly function over that list of characters, and then combine the results using fold of the alternative. But I haven't shown you that definition. I just wanted to show you that my parser still looks very nice and simple. And if I run it, I'm using the maybe monad at the bottom of all of this. Then, given 1 plus 2 times 3, I get just 7 with no input remaining. Sure.
Just kind of, you wrapped up here. Assuming we had applicative and alternative, what we do have the Haskell library, what here did you have to write outside of what Haskell gives you to get to where you are here?
What do I have to write in order to do this?
Yeah.
This line? Okay, 3 lines, I suppose. This class and that instance. Yeah, that's all. Pretty good, huh? Okay. But the whole reason for starting talking about applicative really was that I could do this optimization. So, can I define exactly T for my emptiness analysis? Well, yeah. Does exactly T match the empty string? No. It matches T. So that's easy to define. And as soon as I do, then I can start running the empty parser. I haven't shown you run empty, it's trivial. I can start running things with the empty parser type to analyze my grammar. So can, for example, expression match the empty string? No. I think that's obvious. If I parse 0 or more expressions, can that match the empty string? Yes. So now, my actual parser is, parsing definition is overloaded code, and I can both execute and analyze the same code just by using different applicative functors. Okay. In order to do my optimization, then I also need to know what tokens a parser can accept as the first token. And that's just like defining the empty parser, but a little bit more complicated. So let me define another new type, parser that collects the starting symbols, whose representation is just a list of characters, the list of characters that it accepts. Okay, have to write that, it's boring. How do I recognize, which symbols can a pure X start with? Well, it doesn't accept anything at all, so an empty list of symbols. What about the empty parser? This accepts nothing at all. Clearly, its list of starting symbols is also empty. What about choice? Well, if I choose between a parser that can accept all of these and a parser that can accept all of these, then the result is a parser that can accept the combination. Knob there is just removing duplicates, which I might otherwise get. And what about exactly t? What can that accept as the first symbol? Only one symbol, t. So this is all quite straightforward, isn't it? Except for this clause. Okay, so this is the clause that tells me what tokens an application can start with. So obviously anything appearing in t's can start the result, but what about the things in t's prime? Well, if the first parser can match the empty string, then anything that can start the second can also start the combination. So I need to know here whether or not that first parser can match the empty string. And I don't. What can I do? Let's just leave that out. Okay, I don't know what to write, I'll just omit it. You can do that in Haskell. Of course, it doesn't work. So here's a couple of examples. First of all, let me analyze the grammar exactly x or exactly y. And sure enough, the analyzer says that can start with x and it can start with y. In Haskell, a string is a list of characters, so that xy just contains x and y. But as soon as I take anything that contains star, you know, like sum exactly x, then we're going to try and call a method that doesn't exist, and so we're going to get a crash. Okay, that's a bit of a shame, but I have an idea. If I can't define starts by itself, let me compute empty and starts together. Applicative functors are composable. Excellent. Let me just take the product of starts and empty, so I'll compute both, and I'll define a new functor, static. Static of A will do all the static analysis of my grammar, and I'll just derive a functor instance, applicative, alternative, and a parser instance, and I'm done. Oh well, I also have to explain, because I'm deriving instances for prod. There is no parser instance for prod yet, because parser is a class I've written for this application. So I have to define how to match exactly t in this functor. And of course, what I do is I just use exactly t on each of the two components that I'm combining. Okay, now will it work? Of course not. So what I've done is I've now combined code that doesn't work into a larger whole that doesn't work. And indeed, embedding bugs into larger pieces of software rarely fixes them. But now you can see that if I analyze exactly x or exactly y, I get a richer result. Run static returns a pair of the starter symbols and whether it can match the empty string. And we can analyze this and see that it cannot match the empty string. But once again, if I try and analyze sum exactly x, then that needs to use the apply operation, which I haven't defined, and it's not going to work. But now I have something that almost works. So let me just replace the definition of that star operation for static. And I'll replace it with a definition that does work. So what I have to do then is when I define my static analysis functor, I must not derive the applicative instance, because I'm going to have to write that by hand. Here it is. And the interesting case here is the definition of application for static, because I now have both the starting symbols and the results of the emptiness analysis available. So I can just look at this and compute the starting symbols in the way that I want. Take the first parser t's, and then if that can parse empty, add the second parser t's prime. And the rest of this definition is pretty much boilerplate. I have to compose the empty things as well, but I'll just use the empty star operator for that. And for pure, I'll just use the underlying pure. So it's really this part here that is the critical bit. And oh, what's that twiddle? Every time that I write these star definitions, I have to think about making sure that it's sufficiently lazy. Yeah?
Isn't combining stars and empty not much nicer than these incomplete pattern matches you have here, and these structures are lazy?
Sorry, what incomplete pattern matches do I have?
Well, in your previous definition of applicative, where you sorry, not where you forgot defining applicative.
Yes.
Isn't it much nicer to just combine starts and empty, so you have something like option list of car?
So I think you're asking, is it really worthwhile separating empty and starts into two different applicative functors, which leads me into this problem? Or would it have been nicer, perhaps, just to have taken a pair off? Well, okay, yes. No, a pair would have to be a Boolean and a list of starters, not decomposed the function into two parts.
Because in my case, you would have stronger, you can use your typing system to avoid more errors.
Yes, conceivably, but then I wouldn't have had a chance to illustrate how to pair these together as a product. So it's partly pedagogical.
Okay.
Will you buy that?
Yes, certainly, but we are all used to systems like Cork and Agda, and there we just can't do this.
Ah, my heart bleeds. Anyway, now it works. Here it is. So now that second example is, okay, no, I'm taking different ones now. So if I analyze a grammar that says parse one or more spaces and then x, it says that starts with a space and it doesn't match empty. If I say match 0 or more spaces and then x, it says it might start with a 0 with a space or an x, and it can't match empty. And if I say what characters can an expression start with, then it says 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, or an open bracket. Everything's fine. Okay. I think that's a nice story. It should work, but it doesn't. And I think it's because of a bug in GHC strictness analyzer. So if you write that code, it falls into an infinite loop. And to fix it, I had to explicitly declare the alternative instance 2, taking almost exactly what the deriving clause would have generated, but then remove one of the methods and use the default implementation instead. It's a horrible hack, and I've reported this to Simon PJ, and I hope that by the time anybody tries to do this again, it will work as it should. I just want to tell you that in case you take this code exactly as it is and try and run it, because with the present version of the Haskell platform, then you will hit this bug. Okay, so now I've got to the point where I have a static implementation, static analysis of my parsers, and I can make my optimized version. So if I want to optimize choice, which was my goal, then I can just pair together the static and the monadic parsers. And then I'll have to define a new alternative instance. Here you can see I've derived functor, applicative, and parser. But now I can write the alternative instance that looks at the next token and looks at the possible starter tokens and makes an optimized choice, discarding a parser that would not be used. I'm not going to show you the code for that because I want to show you something else. But I hope by now you've seen enough detail that you can envisage how that would be done. Now's when you say, yes, yes, it's easy. We see how to do that. Okay, well, somebody does. And as I was explaining earlier, this optimization cannot be done with monadic parsers because we don't have the second parser in our hands and we can't inspect it. So static analysis does not fit with monads. Okay, what else can we do? Are there other interesting applicative functors? Well, let me take my random monad that I talked about on Thursday and turn that into an applicative functor. So I'm now going to call that monad random m because I want to call my applicative functor random. So there's a slight change of name there. So let me just define a new functor by wrapping that monad and derive functor, applicative, and choice. What's choice? It's my own new class. So I'm going to define another class for random generation that provides a method that, given a lower and an upper bound, generates an integer in that range. So implementing choice is very easy. I'll just write monadic code once again. So I'll wrap a computation that generates 30 random bits and then maps them into the range m to n. And having done so, I can now write random generators using the applicative interface. Oh, no, I can't. I also have to define a random alternative, of course. So I can make random an instance of this alternative class. And, of course, I don't want to generate two random things and then choose between them. That would be expensive. I want to make a choice, therefore, in the monad so that I can avoid generating both operands. But that's easy to do, too. Here we go. If I take two wrapped monadic computations, then I'll just generate a random value, 30 random bits. I only need one of them. If I get an even number, I'll choose m. Otherwise, I'll choose m prime. Very nice and simple. Slightly less satisfactory is that there's no sensible definition of empty here. Why? Because my random monad always generates something. And empty should not generate anything at all. So, well, never mind. When I write random generators, I rarely want to say, don't actually generate anything. So perhaps that doesn't really matter. OK, here's an example. This is a generator for bounded lists, which are now very easy to define. So blist takes a bound on the list length and a generator for the elements. And if the bound is 0, then it's a pure empty list. Otherwise, it's a bound now, so I'm not going to generate a list of exactly n elements. It may be less than or equal to n elements. So what might blist of n generate? Well, it might generate a shorter list, or cons applied to an element and a shorter list. And the shorter list is just defined recursively with a bound 1 lower. So that was easy. And here's an example. If I run that, again, I'm not going to show you run random, it's easy. Let me make a generator with a bound of 30 elements where each element chooses between 1 and 10 or generates a pure 33. I ran that code, and there is the list that was generated. Cool, huh? Any observations? There are a lot of 33s, aren't there? Well, of course, because my choice operator chooses randomly between the two alternatives with a 50% probability of choosing each. So, of course, we'd expect half of the elements of this list to be 33. It's not always what we want. So those of you who know Haskell Quick Check will know that you can specify weights in order to change this. But by default, if you don't, this is the behavior that you will get. And maybe it's not really what we want. If we write a generator and we say, for example, well, you know, this random list is either nil or a cons with lots of stuff in it, do we want to get nil half the time? Usually not. Can we do anything about that? Well, the problem here is that choose 110 can generate lots of different values, but pure 33 can only generate 1. And yet, we're choosing pure 33 just as often. If only we knew how many values could be generated, then we might be able to make a more sensible choice. Ho ho! Let me see if I can define another alternative functor that will collect that information for me. I'm calling it Cardinality, or card, so it fits on my slides. So it's going to be another of these collection functors that just collects an integer. OK, so let's think about the applicative interface. What's the cardinality of the set generated by a pure generator? Well, 1. It always generates the same value. What about application? Well, if I can generate m different functions and n different arguments, then I've got m times n ways of combining those. What about alternative? Well, the empty generator doesn't generate anything at all. Cardinality 0. And choice, if I've got a choice between m things on one hand and n things on the other, then I've got m plus n choices in total. And then finally, for my choice class, I can just say, choose mn, generates from a set with cardinality n minus m plus 1. And I need a coercion in there as well. So that's very nice and simple, isn't it? I just before you pick me up on this, this is not generating the actual cardinality of the set of possible values. It's generating an upper bound. Why is that? Because even if we generate m functions and n arguments, there might be many different ways of getting the same result by combining a function and an argument. Likewise, for this choice operation, if I make a choice between pure 0 and pure 0, then the generator really has a true cardinality of 1, but this is going to compute 2. So we're counting the number of ways of generating something rather than the number of different values you might get. But it's a good approximation. So now I can just use cardinality to guide my choice operator. Let me define a uniform functor that is a product, again, of my cardinality, which is doing the analysis, and my wrap monad that we previously saw. And I can derive functor, applicative, and choice, provided I explain how prod can implement the choice interface. And the definition is very similar to what we saw before. We just use choose in each of the two functors that we're combining. And now I could show you, I'm not going to show you the code because it's slightly, there are one or two subtleties. But I can now take a choice of generators, find the cardinality of each one, and just weight the choice according to those cardinalities. And a very nice consequence is that I can also define empty in a sensible way. Okay, recall there was no sensible way to define empty for the random monad, but there is for the cardinality analysis. So let me just define empty in this combination to use the empty from the cardinality analysis. Why is this nice? Why isn't this going to break? Because the only interesting thing about empty is how it combines with a choice. So now we know that empty has a cardinality of 0, and that means that the choice will not choose it. So fine, we will never hit that undefined. Okay, there's a test of the old functor, and down here is the test of the new one. And as you can see, 33 still appears, but a much smaller number of times. Also, you'll see that the list is longer. Why is that? Well, you know, if you look at lists with a length bound of 30, actually the vast majority of them are 30 elements long, and this one is 29 elements long. So we'll also get longer lists as a result of choosing with a uniform distribution. So I think that's quite a sweet application of applicative functors too. I want to show you one or two more things. One example that you will find whenever applicative functors are discussed is ZipLists. So the effect of application on lists, there's actually more than one interesting way to define it. And one interesting thing to do is to think of a list as representing a sequence of steps. So if we have functions at 3 steps and arguments at 3 steps, then one sensible thing to do is to create a list of results in 3 steps by applying the step 1 function to the step 1 value, the step 2 function to the step 2 value, and so on. So this is a sensible way to define application on lists, but actually lists are already an applicative functor, and they have a different application that comes from the list monad. So we need a new type. And we can define a new type of ZipLists and define the applicative instance this way. So it turns out that the right way to make a pure value is just to repeat it at all steps, so you get an infinite list there. And then when you apply one zip list to another, you just zip with the application operator to apply every f to the corresponding x. You might wonder, isn't there a monad corresponding to that? So if you've got to the last exercise that I put on my exercise sheet, then you will have been looking at this idea. So it seems that if you have a list of a's, bind f, then when you apply f to each a, you're going to get a number of lists of b's. So if we want the results, the kind of zipped results, look, aren't they there on the diagonal? So it's tempting to write a monad instance that extracts the diagonal of a matrix at this point. And you know what? The type checker will have no objections at all. Everything will work just fine until you run those quick check tests I gave you. It turns out that the third monad law fails for this. So this is, there aren't all that many terribly interesting examples of definitions that are well typed, have the monad type, but don't actually satisfy the monad laws. But this is one of them. And the reason it fails is that my diagram is misleading. Nothing guarantees that f will produce a list of the same length for each a. So it's easy to look at that and think, oh, this is a list of lists. Let's think of it as a matrix and take its diagonal. But it's actually a kind of raggedy matrix. And it doesn't make any sense. Another application of applicative functors is to functional reactive programming. If you don't know this, it's some beautiful work that has been done over quite many years, which describes behaviors that change over time. And conceptually, a behavior A can be thought of as a function from time to A. So you can see that that's naturally an applicative functor. If you have a function from A to B at each time, and a value A at each time, then you can construct a value B at each time. But a monadic interface will be much more awkward and much less efficient, because you would have a behavior A at each time, but then you'd have to apply this function at each time. So you'd have to construct one behavior of type B for every time. And so if you want to know, for example, what is the, the final behavior here, what's the value at time 1000, you'd have to say, OK, construct the value of A at time 1000. Now construct this entire behavior, which will describe a behavior from time 0, and extract from it one data point. And that has turned out to give very, very inefficient implementations that use far too much memory, because they have to store far too much information to be able to construct that behavior, even though only a small part of it is needed. OK. I want to quickly show you one more example. So is it OK if I go on till 10 past? OK, I did start at 10 to. This is a very nice example that comes from Phil Wadler's Links project. So Links aim to provide a nice way of programming things like dynamic web pages. And one of the problems there is dealing with forms that appear in HTML. So up here at the top of the slide, you can see a very simple HTML form in which the user can enter name, age, and gender. And that's generated from some HTML that looks like this. It contains these input fields. In this case, they're all of text type. And every input field has a name. So that HTML is sent off to a browser. The user fills in the fields, clicks submit, and then the contents of the fields are sent back to the server. And by the time they return to the application, they're usually in the form of perhaps a list of pairs of field names and contents. So if you use the interface at this level, it's just a real pain. Why? Well, for a start, all the names in your forms must be unique. So if you start trying to build larger forms and composing a form out of parts, let's call them formlets, then you have to make sure that even though you're composing your form from, formlets that may come from different modules, they all use different names. Ugh, what a pain. Of course, you would like to generate those names rather than to have to see to it yourself that every formlet uses a different name for its fields. What's more, when the data comes back, often there's one piece of code that generates the HTML, but then it's some other piece of code, it might even be in a different file, that processes the result of the form. Those two pieces of code have to be kept in sync. They have to use the same names to refer to these fields. Otherwise, the code that processes the form data won't recognize the data that has been supplied. So this is just a horrible pain. So the idea of the Formlets library is that instead you should be able to combine all of that into one place. So suppose I were to parse that form and I want to end up with a person value. So I've declared a person type up there with just 3 fields, a string, an integer, and a gender. Then I could write, using formlets, the code for generating that form like this. A person is just going to apply the person function, discard the result of simply generating some text, then consume an input field. That's going to be the first argument of the person constructor, and then discard the result of some more text, and then consume another input field and apply Haskell's read function to convert it from a string to an integer. That's the age field, and then discard the result of some more text, and then consume another input field and convert it, in this case, to a gender. Strings. Yes, well, so there is a Formlets library that Phil has worked on, and it does not use strings, but there would just be so much more to explain. So I'm showing you nano formlets, which only provide this business of generating input fields and recovering their values. But you can see that this is now very nice code. It uses the applicative functor interface, and there's no reference any further to the names of those fields. It's all in one file. It's simple. So let's see how to implement that. So we actually need 3 different features. We need to generate unique names. We need to collect together the generated HTML that's going to be sent to a browser. And we also need to specify how to evaluate the results when they come back. And I've written there in this order. And this is interesting because these are each effects, but they have to happen in this order. First of all, we have to generate all of the names that appear in a web page. Then we have to generate all of the HTML for the web page before we start evaluating any results. Why? Because we have to send that HTML to a browser and wait for the result to come back. So only when the result comes back can we do the evaluation and construct the data that we were trying to collect. So we have 3 kinds of effects, but they occur in stages. And with applicative functors, we can naturally express that. Here's my formlet type, which is now just a composition of a name generator functor, an HTML functor, and an evaluation functor. So I've used my compose type here, but basically we're working with things of this type. So here you can see that the first thing, when we run something of this type, the first thing we will do is name generation. Then once we've done that, we can get hold of the HTML. We can ship it off to the browser. After we've generated the HTML and sent it off, then we can get hold of the evaluation function when we need it to evaluate the results that come back. So evaluation depends on the HTML. The HTML depends on the name generation, and that's why we have to compose them in this order. Okay, here's name generation. What are we going to do? We just need unique names. Let's use a counter. We can take a state monad, with an integer state and wrap it. Here's a type. We derive most of the stuff. We just have to implement the name generator. And it's a simple piece of monadic code. It just increments the counter and returns a suitable string. Here's how we collect HTML. I'm going to define my HTML functor just to pair a string with the value. And it turns out that pairing a monoid, like strings, with a value always gives you an applicative functor, and it's in the libraries. So I can just derive those two instances. And then I need to write an operation that actually causes an effect, generates some text. Here it is. This puts a string in the HTML field. And the library code will append all of those strings together for me. And while I'm at it, here's how to generate an input field. You just apply the text thing I've just defined to blah. Don't you just love HTML? How about evaluating fields? I'm going to define an evaluator to be a function from that list of pairs of strings to the value. And once again, a function from a fixed type always gives you an applicative functor. And it's in the library. So I can just derive the instances I need. All I have to write by hand is the function that looks up the value of a named field. Here it is. Take the name, use the Haskell lookup function on lists. It returns a maybe, strip off the just. I'm done. So now I come to the formlet type. There was the type definition I showed you. Once again, I can just derive the functor and applicative instances. But I have to define the operations that you saw in that code. I have to define how to generate HTML. And of course, I'm going to do that with text S. But that is